I explained the input and output impedances of voltage shunt feedback amplifier. Okay, in the last two videos I explained how to find the input and output impedances of voltage series feedback amplifier and also current series feedback amplifier. Okay, now we'll see about voltage shunt feedback amplifier. Okay. Input and output impedances of voltage shunt feedback amplifier. Let me draw the block diagram of this voltage shunt feedback amplifier. Yes, amplifier. And the feedback network of factor beta. Yes. So this voltage shunt feedback means sampling is voltage and the mixing is shunt mixing. Okay. So we know the voltage sampling concept. RL. Yes, the total output voltage is connected to the feedback network in parallel. Yes. So the voltage across RL is V0. Okay. And then, yes, what is the shunt mixing? We know shunt mixing. In the case of shunt mixing, the input is current source. Okay. Yes. Current source, IS. Okay. So this is shunt. This is your shunt mixing. Yes, this current exactly to the amplifier is II, and the feedback network mix the feedback current with the input current. Okay. So feedback is negative, so you must indicate the direction of IF like this. Actually, you must indicate any current upward, but it is negative, so you have to indicate in downward direction. Okay. So what is the input of the feedback network? V0. Because output is voltage. What is the output of feedback network? As the feedback has to mix with the current, it is current IF. And what is IF? IF is equal to beta V0. Fine. Another point is, so what is the amplifier output? Voltage. What is the amplifier input? Current. So what is the gain of the amplifier? A is equal to output voltage by input current. Say this. Voltage by current is nothing but resistance, and as these two parameters are, one is for output and another is for input, this is called trans resistance amplifier. Okay. So what is the amplifier? The amplifier is trans resistance amplifier. Okay. So now this will be indicated by RM. RM is equal to V0 by IA. And we know this is RM is gain without feedback. If you want to find the total gain of this amplifier, it becomes RMF. RMF is equal to RM by 1 plus RM beta. Yes, I already explained in the concept of types of feedback amplifiers. Okay. Yes, if you want, you can go through that video. Okay then. Now to find the input and output impedances, so we need to draw again the Thevenin's equivalent circuit. Yes, so the input is current. Yes, another current is there in the opposite direction, that is IF. Yes, here you have the resistor Ri and the current through this Ri is II. So this is about input circuit. And coming to the output circuit, it is, what is this? Voltage sampling. Okay. Yeah. Yes, you can use that voltage series feedback output circuit. Okay. So what is that? So voltage sampling. So this must be a voltage source. What is that? RM, II. And then you have the resistor R0. And then, yes, here is your resistor RL. Okay. And the voltage is V0. Fine. So, if you remove IF, then it will be simply the Thevenin's equivalent circuit of trans resistance amplifier. If you add the feedback like this, then this becomes the equivalent circuit for voltage shunt feedback amplifier. Okay. So then, yes, let me find the input impedance. Yes, I already mentioned one point. While finding the input impedance, you must write the equation. It may be KVL and KCL depending on the input circuit. You must write the equation for input. So now if you observe the input circuit, yes, it seems to be a circuit in which you can write KCL. Okay. So now what is this KCL? See here, IS is coming to this node. Okay. Then it gets divided like this. Fine. So now we'll write the KCL. Okay. So input KCL. So what is the input KCL? IS is equal to II plus IF. Okay. So what is this IF? Yes, already I've written IF is equal to beta V0. Yes, what is this IF? Beta V0. And I'll mention here RIF also. What is RIF? Yes, the voltage is VI, because this is your VI. There is no change for your voltage as all are in parallel. VI by IS. Okay. Yes. Now I'll substitute IF, that is beta V0. Okay. So now you have to modify or you have to write what is V0 with the help of output circuit. Okay. So from the output, yes, again you can write it as, yes, it seems to be a circuit in which you can apply voltage division. So what is V0 actually? It is the voltage across RL. Okay. So there exists a total voltage source, a dependent voltage source of RMII. It gets divided into two parts. One is across R0 and another one is across RL. Okay. So what is V0? So V0 is total voltage RMII into that resistance, yes, RL divided by RL plus R0, means the sum of resistances. Okay. So what is this amplifier? Trans resistance amplifier. Yes, you must recollect that concept of the first video. Yes, for the trans resistance amplifier, the input and output impedances are very low. LL, the code is LL. Okay. So as the output impedance is very low, so as R0 is far less than RL, so what you can do? Yes, you can neglect R0 and then you can cancel RL. Okay, so it implies what is V0? V0 is RMII. Okay, so V0 is RMII. Then just yes, now you write this IS. Substitute V0 equal to RMII in IS. So what is IS? IS is equal to II plus beta into RMII. Okay, so now II of 1 plus RM beta. Okay, so then RIF, therefore RIF, that is VI by IS. Yes, simply you substitute IS, VI by II of 1 plus RM beta. Okay, so what is this VI by II? VI by II is nothing but, yes, it is nothing but RI. Okay, so what is totally RIF? RIF is equal to Ri by 1 plus Rm beta. Okay, yes, this is your input impedance of voltage shunt feedback amplifier. Okay, so in the absence of the feedback, the input resistance of the trans resistance amplifier is Ri. But when you apply the feedback in this fashion, then automatically the input impedance decreased by a factor 1 plus Rm beta. Okay, so then we'll see output impedance. Okay, so what you have to do to find the output impedance? As the input is current source, you must open and then you disconnect RL. You have to assume a current and voltage there. Okay, so now let me open this. Yes, if you open, yes means you made Is is equal to 0. Okay, same way here also you just open, means the disconnect RL. Yes, assume a voltage V here and assume a current I, and yes, this current is I0, that is IL, which is equal to minus I. Okay, so then yes, you must write the output equation first as you are finding output impedance. Okay, so first write output KVL. Okay, see here, as I is coming like this, you must take the terminals like this. We already know it. And the terminals of V are like this. Okay, so you just write KVL, you start from the second sign, yes, plus RMII, okay, then second terminal plus IR naught, and here also the second one minus V is equal to 0. Okay, so then what is I? I is V minus RMII by R naught. Fine. Yes. Now you must change this II. Means you must write an equivalent for II from the input circuit. Okay. So from the input circuit, as you made Is is equal to 0, what is the input case here? Yes, it becomes, the input KCL is, yes, II is equal to minus IF, because Is is equal to 0. Okay, yes, what is this IF? IF is equal to beta V naught. So minus beta V naught is nothing but, as V naught and V are same, it is simply minus beta V. Yes, substitute this II in this expression. So we will get I is equal to V. Yes, this minus becomes plus Rm into beta V divided by R naught. So now you take V common, 1 plus Rm beta divided by R naught. Okay, yes, what is R naught F here? Yes, see here, this is your R naught F. Yes, as usual R naught F is V by I. Okay, so now from this, your R naught F is, yes, V by I. We just simply take this I at this place, so it becomes V by I. So now what is R naught F? R naught F is equal to R naught by 1 plus Rm beta. Okay, so this is your R naught F expression. Okay, so what is this? Yes, in the absence of feedback, the trans resistance amplifier output impedance is R naught. But when you apply the feedback in this fashion, the output impedance is decreased by a factor 1 plus Rm beta. Okay, so now if you observe these two impedances, input impedance is decreased and the output impedance is also decreased by a factor called desensitivity. We know the desensitivity is 1 plus Rm beta for this amplifier circuit. Okay. What is the circuit? Voltage shunt feedback amplifier. Okay, the sampling is voltage and the mixing is shunt. For that type of amplifier, both the resistances are decreased. Okay, so this is about the concept. Thank you very much. Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.